Okay, my name is Vince Ugarow. I'm a chartered design engineer working at an engineering consultancy called Hilton Moran. First of all, you may not recognise that his surname is not very English. Quite complicated. My grandfather was actually born in Riga in Latvia, but my family come from what used to be the old part of Poland, but now it's part of Ukraine. So it's all very complicated, but I was born in England, but I still have a lot of heritage from that part of the world. In terms of Hilton Moran, as I said, we are an engineering consultancy. We are based in the UK. I work in the London office, which is the biggest office, and we are MEP, that's mechanical, electrical and public health design engineers. And we work across many different sectors, from offices to residential to retail, also to some laboratory works, also big master plans, also in the UK, but also in the Middle East, also in Europe, and now we are doing some projects in North America. So it's quite a wide sort of variety. But today I'm going to sort of specifically talk to you about some of the design challenges that we face when designing tall buildings. Of course, a lot of the systems are very, very similar to much smaller buildings, but there are some specific challenges that you should be aware of when you are designing tall buildings. So first of all, I guess in terms of building performance and efficiency, our view is this is equally as important as the architect wishes for a building to look like. In terms of its aesthetics, the quality and the iconic status of buildings. And you may ask yourself, well, why is this? Well, the reason is it has a direct impact on our environment. And particularly tall buildings, it has much more bigger impact, particularly in the local area. So, for example, if you look at the environmental challenges, there's landscape, there's the public realm, there's challenges on energy, on water, on the air quality, and also the ecology around that area where the tall building is going to be located. But also there are some other sort of impacts. First of all, socio and cultural developments. You can see that, for example, in the Middle East, where there are lots of tall buildings now, that's more of a political statement. Things like culture, religion and media also come into play with tall buildings. And if also things, for example, in lots of countries, tall buildings become an iconic status which actually feeds into tourism and more economic arguments for it. So there's a lot of different areas that impact what tall buildings actually do. So why is that important? Well, the reason is if you don't consider all those factors that I talked about, you get uncontrolled development. So this is a picture of Manhattan in New York, and you can see that there was no master plan in the early days. It was literally just put up a building as high as you can, right next door to someone else, without any regard of the environment around it. Of course, this is what happens when you don't look at the infrastructure around buildings. So this is an image of a roundabout in China, where they actually put up a lot of constructions of tall buildings. And you can see that without proper infrastructure for transport, this is the result of what you get. And it's interesting because, for example, in London, the planners have actually stated that they actually would like tall buildings to be built around major transport hubs. So big railway stations or big metro stations, that's the place where tall buildings should be located because they have less of an impact on the surrounding infrastructure, surrounding traffic, etc. So what I want to do today is talk to you about some of our design principles, our design approach, Some of it is sustainable features, others is more practical. And also, I can give you some insight into a case study, which is a tall building which was completed about 3 years ago in London called 20 Fenchurch Street. Some of you may know it by its nickname, which is called the walkie-talkie. But I can show you some more details about that as we go through the presentation. So first of all, our approach when looking at designing tall buildings, and in fact any building actually, is to follow this energy hierarchy, where the most important thing is to start at this bottom tier here. In other words, to look at the mass and the built form of that project, because that will have the biggest impact from a sustainable point of view on the building. So if you can influence the orientation of the building, the shape and the fabric, you immediately want some big plus points. And again, I find it interesting that perhaps 20 years ago, when we were working on projects as MEP consultants, we were brought into a project quite late. By then, the architect has already perhaps designed the principles of the building. It's probably gone to the authorities to get the planning permissions, and then they say, Mr. Engineer, come over here and can you now design all the systems? Of course, now you can't do that. We have to be involved right at the beginning, and this is an area where we can actually make some real differences. So after this first level, the next level that we can have a real influence is the facade, the design of the facade. Again, obviously the look for an architect is very important, but it must function correctly, it must function the most optimistically, so that's a very important area. The third level is designing energy efficient systems, so the lighting, air conditioning, what we call mixed mode, and that's where potentially in certain climates, why not have the ability for the occupants to open the windows at certain times of the year. And of course the controls are now becoming more and more important and sophisticated. The fourth at the top, almost there, is then the infrastructure. In other words, how does that energy get to the buildings? I know in most European countries, district energy has been here for a long time. In the UK, that was not the case, but it's now starting to change. So we have many district heating plants, which now the planners require us to actually make sure we have connections to those. And at the very top is you can then consider on-site renewables. So photovoltaics, solar, wind, and also a technology called fuel cells, which I can explain to you a bit more about, because that is one technology that we used on the case study at 20 Fenchurch Street. But I think the important message here is there is no point considering number 5, the on-site renewables, until you actually challenge yourself on all these other questions. So this is really our design approach. So I'm going to just concentrate on 3 areas here. One is about wind studies and their relationship to tall buildings, the solar analysis, and then also just a bit about the facade performance of buildings. So first of all, in terms of the wind conditions, this can actually influence many things about tall building design. Its orientation, the actual building form, and also the actual shape of what we call the leading edge of the building, which is where the main prevailing wind direction hits the building. You can see here, this is an image of 30 St Mary Axe, which is known as the Gherkin in London. This was one of our first tall building projects, which has now been completed 12 years ago. And it was a very successful building of its time. In fact, the units, we had Swegon gold units in this building. which were installed above the ceilings on every floor. So it was a decentralised ventilation strategy. And we actually also did a lot of thermal modelling and wind study modelling to look at how the wind behaves as it hits the building. Of course, when you do this type of analysis, most of tall buildings do actually go through and they are actually put into a laboratory condition where we do wind tunnel tests. So you can see here this image. This is a model of a tall building, and you actually put it into a chamber with big fans, and you actually start seeing the behaviour of the wind pattern on that building. This is quite a useful visual sort of test to see how it performs. The only problem with this is first of all, because of the scale of the model, the results you get are not very accurate compared to a full-size building in real life. It also is quite costly to set up these tests, and so what we focus on now is before a building goes into a wind tunnel is actually to simulate this by using CFD, which is Computer Fluid Dynamic Analysis. This is a powerful software programs where you can actually put a 3D map of your building into the computer model, and you can start simulating wind conditions and just seeing what happens or predicting what happens to the wind as it moves around the building. Of course, what this can do is you can actually see how this behaves when there are other tall buildings around the one that you're designing, which has a massive effect on the performance. In fact, in the City of London, the authorities insist that you do this test before you put the building in for planning approval. So every tall building in the City of London has to do this type of analysis. So in terms of the building form and its shape, this is some of the results that we were finding, where the one to really watch is that if you have a building in a square form, which is just a single block with very flat sides, the prevailing wind direction is from this end here, and you can see that as the wind hits that flat facade, you have 25% of the wind actually gets pushed upwards, okay? Only 10% moves around the building, but you have 65% of the wind which actually goes into downward direction. And there are many examples, mainly in the States, in America, where this issue causes big problems at street level, at the main entrance as you walk into a building. You get some very, very high wind pressures. And so, by doing this analysis, you can see that rather than having a very flat surface, if you slightly curve it, you can reduce this wind loading quite substantially. The other area where you can see a lot of tall buildings designed now is at the ground level, you have some form of a canopy above the main entrance. So any of the wind that falls down the building gets deflected off the canopy. And that's a very common design approach to negating the issue with wind. And this is a good example of a project which we were involved in the Middle East, in Abu Dhabi, about seven years ago now, where we simulated the wind conditions around a very tall tower, 73-story, 300-metre tall tower, and also a neighbouring residential building here. And you can see how the various arrows here behave with the wind velocities. So where you've got this sort of yellow white areas, the wind was reaching 6, maybe up to 7 metres cubed per second, which is quite strong. So this analysis was very useful for the architect to plan what happens at street level. And so this was really useful piece of information for them. The other area which again becomes very useful is the analysis of the solar performance and the solar analysis of the building. So by doing sun path studies around the building, you can influence the facade design and also the thermal comforts of the occupants who are going to be in that building. And here is an example of one which we carried out a few years ago on a new development called Elizabeth House in London. The building was quite complicated, had a 29-storey tower and then a few smaller blocks here. And this just shows you where the yellow area, which was south-facing, had the greatest solar intensity. The west area had a bit less, but also by having the computer model put in neighbouring buildings, you can see where some of the facades were being shaded by other buildings. So all this information is very useful for the architect to start thinking about how to design the facade. And you can have different designs depending on whether you're the south or the west or indeed the north. And I'll show you later an example on 20 Fenchurch Street, the case study, where there are actually different solutions depending on which facade you are looking at. Of course, the internal environment for the occupants is also very important. Daylight, thermal comfort and air quality are probably the three biggest factors that we need to consider. And I think this is something that's interesting. We're finding a trend now mainly for commercial office buildings, where previously the focus was on the performance of the building, where I think now there is a change of emphasis to really think about the people who are occupying the building. You know, that's more and more important. And we are finding now that building assessments, for example, BREEAM or LEED, they are still important, but there are now new assessments being introduced which now focus on the occupants, not the building itself. So, for example, there's an American assessment called WELL, W-E-L-L, which I don't know whether you have heard about, but this is now becoming, we are finding much more important as opposed to BREEAM or LEED. I mean, interestingly, talking about BREEAM, I don't know whether you know who was the biggest person who influenced BREEAM. And actually the answer is it was the Prime Minister at the time, who was Margaret Thatcher. She was responsible for BREEAM. The reason for that is, if you look at the letters B-R-E at the front of BREEAM, that stands for Building Research Establishments, which used to be a government organisation in the UK. And of course, when Margaret Thatcher came into government, she privatised a lot of industries. And one of the areas she did privatise was the BRE. It became a private company, not a public company. And of course, at the time, they had to decide, well, how are we going to generate money? How are we going to generate an income for our organisation? And that's why they formed the assessment of BREEAM, which obviously, as you know, every BREEAM assessment that you apply, you have to pay a fee, and that's how they generate their income. So it's interesting that Margaret Thatcher is the person who introduced BREEAM to everyone. But anyway, back to workplace. If you look at commercial office buildings, lots of things have changed over the years. It's now not just a place where you go and work and where you come home. The new generation of office workers, they blend and mix their social life and their work life together, and it becomes much more of a 24-hour sort of situation. So we're now finding that you collaborate at work. You get various resources, you learn at work, you socialise at work, and also well-being is very important now in the work environment. So these sort of new trends means that the balance between people working and playing is now being very much mixed together. And of course, it's not unusual to find these different facilities in commercial office buildings now. And again, it was interesting because I was fortunate to come here to Tallinn for one day before this conference, and of course I had the opportunity to have a look and visit, of course, the old town, which is very interesting. But for me, what I found interesting is going to the industrial area, is it Teleskivi area of the city. And that was really interesting what they're doing there, where they're regenerating very, very old industrial buildings, and these are now becoming the new hubs for creative industries. And you know, this is what we are finding also, particularly in London, and also tall buildings are now having to really look and see whether they can appeal to this type of worker, to this type of occupant. So one of the factors in terms of well-being, probably one of the #1 factors we feel is daylight. You know, having daylight where you are working is, from a well-being point of view, very, very important. And so we carry out lots of studies, and this is an example of a study which we did for a large building where we could actually influence the way the building actually worked, the way it was planned. And we started off in this scenario here, which was the first step of the building. Now, these two graphs represent floor plates, typical floors. So we had one floor here and one floor here. And what we could do is build a software program that predicted the amount of daylight that was coming into the floor plates. In other words, you can see here that near the window, there's a lot of daylight. But as you move deeper into the building, that daylight tends to drop off. And one of the measures that we use is what's called daylight factor, 2% daylight factor, which is a measure of any space which has good quality daylight. So that was our benchmark. So you can see here that the sort of yellow areas, which is around the perimeter of the building, had good quality daylight. And so, you know, this was one floor, this was another floor, you know, just to get a typical example of both. So you can see that for the complete floor plate, we were getting about 40% of the area had very good daylight. So how can we improve that? So the first step we did is we introduced some light cuts into the facade. So you can see here, we pushed the building inwards, and also here, compared to here, which means that you get just a little bit more daylight coming into the building. And so that increased the daylight to 43% of the overall area on the floor had better daylight. The next area we challenged was that in these scenarios here, as in most typical buildings, we found that, in fact, in this area, the cores, which are these areas where all the services go up, were on the sort of the left-hand side. But by moving the cores into the middle of the building, you can see that now this space here also has very good daylight. So now we move to 52%. And then, of course, one of the things we did there was that this was looking at the daylight on the actual floor level. But of course, most people in buildings work at desk level, so we can choose the level that we're looking at. So we simulated the same here, and we found that we could get 68% of the whole floor plate so that anyone sitting in those areas had very good quality and access to daylight. And this was an example where us as consulting engineers could really influence the form, the shape of the building. The other interesting sort of study that we carried out on the same building was that if you look at the facade of buildings, lots of buildings have 100% glass, and you can see that in many different scenarios. But of course, you don't have to have 100% glass. Why not go for 50% solid construction and 50% glass? And here we were playing around with different percentages of glass and solid, and then simulating the energy performance of the buildings. And we found on this particular project, what was interesting is that the energy, when you have 100% glass, we had lighting, the cooling energy and the heating. As you move to 50% glass, you got quite a lot of reduction, particularly in the cooling and also heating. But of course, if you move that even further to just 30% glass, that trend started reversing. In other words, the cooling profile actually started going up again. Now, the reason this was happening was the internal heat gains that are generated by computers, by occupants. You know, this is energy that you need to get out of the building. So of course, if you start making it too solid, that heat is actually trapped inside the building. So we actually found that, you know, that the optimum was somewhere about the 50%. So again, this is all very good information that we can feed to the architect so that when they start looking at the facade, that's what they should be aiming at. Not this and not that. And this is an example, as I said to you earlier, of the influence that we had on the project 20 Fenchurch Street. And you can see that it's not one answer for all four facades. It depends on the orientation. So for example, if you actually look on here, this is the north facade. That's just 100% glazing. There is no external shading, because you don't need external shading on the north face of the buildings, or certainly in the northern hemisphere at least. You can see here on the east facade we have vertical fins, and likewise on the west facade. And this is because the angle of the sun is a lot lower, which means that it penetrates the building much deeper. So having horizontal fins on the east and sort of the east and the west facade it doesn't really do any good. And that's why these are vertical. Of course, on the south facade is where you have the most solar intensity, and you can see here these were vertical slats which reduce the solar impact on that elevation. The other area which we also study is to do with human comfort studies. And one of the areas we look at is something called operative temperature, which is different to air temperature. With air temperature, you use a thermometer or a sensor and you can measure what that temperature is. But of course, you can be uncomfortable even if it's telling you that it's 21, 22 degrees. And that's because there's lots of influence from radiant effects, whether that's a cold glass panel or maybe something hot. That doesn't influence your human behaviour and your comfort. So we tend to focus on operative temperature, and the limit there is about 26 to 27 degrees. So that's not the temperature you measure, but it has also the effects of radiance and air temperature on them. And this is really where, if you're starting to look at facades, this is the difference between the G value and also the U value of the facades. And the two, you have to look at both together, depending on what you're looking at, because it's a balance between the heat gain from outside in, and also the heat loss from inside to outside. And this is particularly important in commercial office buildings. Like I said before, in those commercial office buildings, there's a lot of heat that's generated inside the building through computers, lighting, etc., which needs to get out of the building. And so really what you need to do is look at the temperature profile of which environment you are actually working in. So this is just a typical air temperature data that's available, and you can see the difference between the temperature in London with an average, maximum, minimum, and for example in Tallinn, which has got much more extreme temperatures. So it's important to know which part of the climate you are looking at. Now, of course, in hot climates, it's a very different scenario. And what you find there is that facades need to limit the actual amount of solar energy that's actually hitting the building. And so, in fact, that was sort of probably done a long time ago, which traditional Arab buildings were sort of looking at what they call the Mashrabiyah principle, where they have solar shading, which limits the amount of solar intensity that comes into the building. And of course, this is a good example of those principles that are now applied to modern buildings in the Middle East. Of course, in colder climates, this is where solidity becomes much more important, because you have those thermal properties of solid panels mixed with glass panels. So there's a different approach that can be taken. But of course, you also have temperate climates, which I would call the UK, which is sort of not hot, not cold. I think this is a good sort of summary of good facade performance, where in hot climates, external shading is very important to reduce the solar impact on the buildings. In cold climates, consider more solid percentages than glass. And then in temperate climates, it's the G value that really is the dominant feature and characteristic of those facades. Of course, there's also triple ventilation facades. A few years ago, this was quite popular as a design solution, but we are finding this now less so. Two reasons. One is it's very costly, but I think also secondly, the technology now in double glazed facade units has got very, very good. A lot of the big manufacturers of glass have produced transparent glass, which has got very, very good properties of G value and U value. Of course, the other thing is, I've talked about daylight, the other one is air quality in buildings. And, you know, it's interesting that there's a lot of focus generally on what we eat and what we drink, but of course, you know, we also need to breathe. And air pollution is becoming a big topic in most countries now, and I think more and more people are becoming more educated about the implications of air pollution. And these are just some of the sources of air pollution that you can get, which obviously you can see in industry is a big area, but there's also lots of other sources of pollution that are available in industry. And it's now becoming a known fact that probably the two biggest harmful pollutants are particulate matter down to PM10 or even PM2.5. That's very, very small particles that are in the air. And the other one is nitrogen dioxide, which any cars that run on diesel or lorries that run on diesel have this profound impact on air quality. And it's interesting, in the UK, probably about 6-7 years ago, the government was encouraging people to buy diesel cars because they said it's environmentally friendly and gets rid of petrol cars. Of course, now it's completely changed. Now they're saying, don't buy diesel cars, buy electric cars. And in fact, even 2 weeks ago, the mayor in London has imposed a new tax on old diesel cars. So anyone driving into London now who has an old diesel car has to pay additional congestion charge. So the whole thing is now reversed. I think there's a lot more studies available now saying these are really sort of big issues. So of course, how does this affect us in terms of the air quality in buildings? This was a study which we did on a large building in King's Cross area of London. And you can see here, this is the sort of the floor plan of the building. And the first thing we did is we actually started to monitor the air quality around the building and even on the actual site of the building. And what we wanted to do is gather data on PM10 particles and also nitrogen dioxide. And we are still there. We've got these monitors, which are these probes, which are dotted around the whole site. And we've been measuring this now for 5 years. And you can start seeing the plots that we've started to come up with in terms of particulate matter. We weren't surprised by the results because it's not unusual for having average pollutants of 40 nanograms per metre cube in urban areas. That's not a surprise, but of course we do need to now think about how do you clean this up. So what's important is you consider the concentration of particles, but also over what time period. So it's the length of exposure that you have for those particulates. One without the other is meaningless. You have to look at the two together. And what we were interested in is, could you use this as a measure for having a building where you can actually open the facades at different times of the year? You may recognise this image. This image is the gherkin, which I showed you earlier. But I bet most people don't know that that actually has openable facades, because our original design was for this building to have openable facades, so that at certain times of the year you can actually have natural ventilation. This is a very rare photograph because this is not now used at all. The building is sealed. And the reason for that is when we were designing this building 12 years ago, it was actually for an owner-occupier, a big insurance company called Swiss Re. It was their building for their people, and this is what they wanted. Of course, since it was finished, they sold the building, and now it has multiple occupants in the building. And the way this system works, because the floor plates are now all separated, unfortunately the original scheme doesn't work. So it's interesting how that works. But I think what we were looking at is, for certain periods of the year, can you have the window open? Now for this, you have to monitor air temperature, but now we can measure the air quality. So if the air quality is good, why not open the windows? And so this is what we're now looking at in terms of allowing a mixed mode operation of buildings. Of course, when the building is actually sealed, you do rely on mechanical ventilation. And again, we're doing an interesting study with Swegon on this particular project. to see whether we can use floor standing gold units, but actually introducing some very, very high filtration levels up to F9 standard, together with nitrogen dioxide absorption filters, which could be inside the units. So that these two efficiencies of filtration actually then provide very good quality air inside the building for the occupants. And I think we're going to be seeing a lot more of this type of sort of application. I mentioned to you earlier about WELL, which is this new standard, and what it looks like is it looks at these different categories: air, water, nourishment, light, fitness, comfort, and mind. And these are all categories to do with your person as your well-being. So it's a very similar application to BREEAM, but instead of concentrating on the good performance of buildings, it really focuses on the individuals in those buildings. And so what we did is we were starting to train our assessors to be well assessors, very similar to BREEAM assessors. But we thought we need to have a project where we've actually carried this new standard on. And so we decided that our own new office, which is in this building in Manchester, in the north of England, which we have on the 5th floor, we decided to do a well assessment of our own office. And it was a very interesting project to do. We learned a lot about the whole process of doing a well assessment. But of course now we have the knowledge to go and convince clients in other buildings that they should actually be looking at this new assessment. What I'm going to focus on now for this next part of the presentation is more on the practical design features that you should consider when you are designing tall buildings. This is particularly on the mechanical and the ventilation side. So we'll talk about plant strategy, also tenant requirements, focus on cores and risers, and a bit on system hydraulics. So first of all, I think it's true to say that without any restrictions on height, any client or developer will build as high as they can until the cost of building, the actual building, meets the income that it will generate for them. So the net to gross floor efficiency becomes really critical. So every half a metre you can save on the core generates rent for the developer. So it really becomes a very critical item. And in terms of central plant strategies, these are just 4 diagrams that really show you what we believe is sort of the optimum plant floors where you put the mechanical equipment to service the building. So you can see here this is a 35-storey tower, and we are suggesting that you have a plant level towards the bottom of the building, maybe at level 2, and you have one on the roof, so that your big air handling units, which are this level, can serve all these floors up to about here, and then you have some ventilation units at the top, and they serve these floors down there. And somewhere in the middle is where you meet. Of course, when you go up to about 50 floors, this is where you may need to introduce an intermediate plant floor. So in other words, this bottom floor, the ventilation units serve up to about this level here, about level 20. So level 20 serves upwards to this level, about 35, and then of course the roof will serve down. So that's quite a good rule of thumb, a good idea in terms of that size. Of course, when you move up to 65 stories, A similar principle applies, but perhaps you put the plant floor at level 40, and you can see here the same ventilation supplies principles to serve the floors applies. Of course, when you get to 80 floors, that's when you have to start introducing more floors. So here we have a plant floor at level 20 and another one at 55. I think this principle holds the higher up you go, so you just keep repeating this, up to 100, 150 floors if that's how high you are looking at building. Of course, when you're looking at this, you also have to coordinate with a lift strategy. On these tall buildings, although the technology and lift design is improving, you still need to transfer at different levels. So of course, transferring where you've got plant floors is the ideal scenario. Of course, I mentioned earlier about tenants, occupants in commercial office buildings is changing. They're now requiring much more facilities to be provided for them. And I think when you've got a small building, it's probably easier to retrofit, to put in those facilities for them after perhaps a tenant has moved into the building. Of course, in tall buildings that's not possible, particularly when you've got several different tenants all occupying the same building. So when we are designing the tall buildings from the beginning, you have to think about these requirements and actually build them into the building itself from day one. And here are some more examples, particularly electrical communications is another big area. So the infrastructure has to be there, installed day one. The other area you should consider is hydraulics. In other words, heating and chilled water. Distributing that in tall buildings is very important. Of course, because of the height, you're now dealing with pressures which are more than your standard PM16. You could be looking at PM25 or PM40 equipment. Sometimes high pressures systems are good because they limit the temperature drop through circuits. But of course, when you're looking at equipment, it becomes very expensive. And here is an illustration of a very simple isolation via a valve, which you would install in heating or chilled water systems. And you can see the big differences between PM16, PM25, which is rated at 25 bar, or PM40, which is 40 bar, is first of all, look at this is the pipe sizes, 300 diameter, 400, 600. Look at the weight and the cost differences between the two. And that's just for a very simple valve. You imagine when you have bigger pieces of equipment, if you don't get the strategy right, the cost of installation can be very, very expensive. The other thing you have to think about is plant replacement. Of course, tall buildings, they'll be there for 60 years, maybe 100 years. Of course, the equipment that goes into buildings may only last 15 years, maybe 20 years, if you're lucky, 25 years. So you can imagine throughout the change of that building, you'll be replacing this equipment. So how do you do that? Our view is, look at the goods lifts. This is lifts that are installed in buildings to bring up equipment or any goods that are needed by tenants on their floors. So it could be furniture, it could be photocopiers. They tend to use the goods lifts for those. What we found is, if you have a 3,000 kilogram rated lift, you can actually use that for removing and replacing most of the equipment, including air handling units, which then of course you break down into smaller sizes. Risers, again important. This is just demonstrates to you roughly the percentages of services risers that actually occupy space within a core. And again, it's important to get those in the right locations. The other thing to consider is any prefabrication. So are there any elements that you can prefabricate in a factory, off-site, and bring it to site either fully assembled or part assembled? I'll show you quickly a case study of 20 Fenchurch Street, which brings in some of those particular elements. So you can see here, this is a building in London. It's 38 floors high, just under 64,000 square metres of offices. And at the very top of the building, up here, is a public space. So anyone can go up there from the public, and it's a big glass-covered landscape garden with restaurants and a bar. And it's become very, very popular tourist attraction. And it was something that the Mayor of London was very particular about, making sure that there was access to the public at the height of buildings. And what we're finding now is all new tall buildings in London have a very similar facility. So this is a typical floor plate of the building with a core in the middle. And you can see that's where the toilet blocks are. We have 7 double-decker passenger lifts, so that's 2 lifts on top of each other that move together. One serving even number of floors, the other serving odd number of floors. Of course, all the different types of lifts, and of course the MEP risers. Here are some of the headline design criteria that we had to work for the building. Lighting was 12 watts infrastructure, but of course we now design at about 5 watts because of new technology, LED particularly in terms of light fittings. And of course there were some other enhanced features that were allowed. In terms of ventilation, we have provided 2 litres per second per square metre to all floors. In addition to that, there's another 30 litres per second for things like tea points or small catering facilities. And we also introduced 4 large kitchen extract ducts. A lot of the tenants want their own catering facilities in their offices. And so this was provided day one. And this is the plant strategy that was adopted. So we had a ventilation level plant room at this level here, level 2, and one at the very top of the building. And of course in the basement was all the other big plant items, including boilers, chillers, and water tanks. There was a small building next door, which was also connected underneath in the basement areas to the main building. And that also housed generators and additional cooling facilities. This is a typical core layout. This shows you the 7 lifts in the lift lobby. That's 1 goods lift, there's another. These are 2 firefighting lifts. And then of course here are all the mechanical risers on one side and on the other side. So it means every floor you can actually split into 2 and have 1 tenant on one side and another tenant on this side. In each corner we have supply and extract ventilation ducts. Again, to save space, this very corner supply duct, we use 2 sides of the concrete riser to form 2 sides of the duct. So this was galvanised metal, so was this, but this was concrete. Again, to save space. And this was one of our first projects which we did in BIM. And this image is all the MEP services that make the building work. And when we first produced this diagram, it was quite shocking, really, because I think before then, not many people, particularly other professionals, whether it's architects, structural engineers, or even clients, realised how complicated and how coordinated the MEP design has to be. And by producing these diagrams, all of a sudden we can actually now visualise what that is. So I've just picked out some of the key features. So you can see here, these are the big air handling units that serve halfway up the building. And you can see at the top there, there's the other air handling units that serve down. You've got cooling towers, and of course in the big basement area, you have a lot of the boilers, etc. One technology, low zero carbon technology we apply to this building is a fuel cell. Now, a fuel cell is interesting technology because what it works on is, I'm not going to go into the specific details, but within inside the unit, you basically have a chemical reaction which is driven by natural gas. So in other words, this fuel cell is supplied with natural gas. The chemical reaction generates electricity and also generates waste heat. And that waste heat is what we use for driving absorption chillers and also heating and hot water in the building. It's a technology that was invented and used by the American military, and also South Korea as well have been using it. So we found that by using a 300 kilowatts fuel cell, we've actually reduced the carbon emissions of our building by 6.6%, which is actually a very high proportion. The other technology we have is roof-mounted TVs. These are mounted on top of the roof, as you can see in this photograph. And again, these generate 27,300 kilowatt hours per year of electricity. Again, in terms of the cooling resilience, this just shows you we had an absorption chiller, water-cooled chillers, which were in the basement. In addition, we had even more chillers for critical services that is a completely independent circuit, which is also provided for the building. And in terms of air conditioning on the floors, we designed the infrastructure that a tenant can choose whether to have a fan cooling system or chill beams. It's up to them, they can choose what they like. And the way we did this is, we have the two main risers, chill water and heating, but on every floor we actually installed a small heat exchanger. So that's separated hydraulically the main riser from what's happening on the floor. And so the tenant can choose to connect either fan coolers or chill beams to that particular floor. So sort of coming to the end of my presentation, I just wanted to finish on an interesting trend which has been spotted, going back to the 1930s, and it's the economic cycle where in 1930 there was the Great Depression in America, and yet that was the time when the Empire State Building